So we're going to have a look at 10F transferring energy and go straight on to 10G power, because they actually work quite well together, and there's only a little bit on both. So first of all, looking at the equations, energy equals power times time. We already did that in paper 1. We've done it in chapters 8 as well on work and power. So it's the same equation, just general energy transfer is equal to the power of a device or a machine, for example, times by the time. So energy measured in joules, power in watts, time in seconds. And we're going to introduce a new equation for energy transferred in an electrical circuit specifically. So the energy transferred by an electrical power supply, for example, or to a device or component in the circuit is equal to the amount of current in the circuit times by the voltage of the supply or the share of that component times by the time. So increasing the current in the circuit transfers the amount of energy that's transferred to that component. Increasing the voltage of the supply, for example, also increases the amount of energy transferred to that component. And then if you just have that going over a longer period of time, then the amount of total energy transferred will increase as well. So they're all directly proportional. I, V, and T directly proportional to energy transferred. Okay? We need to also have a look at, for transferring energy, the resistance in the circuit. So resistance occurs, we know that it's the slowing down of current by a component, but now we're talking about the resistance in the wires themselves. So the resistance occurs due to collisions between moving electrons and positive ions. If you have a look at this diagram, you've got a lattice. We know that metals that are used for circuits and wires generally tend to be metals of positive lattice of positive ions, and then electrons that can freely move between those ions. Now if you have a look at this diagram, they're your positives, your electrons are passing through those ions around the circuit inside the wire, but there's going to be some friction, there's going to be some collisions between the electrons and the positive ions, causing the heat to be generated and that resistance to occur. So we need to think about how can we reduce the amount of resistance that occurs in an electrical cable, for example. So number one, you can make the wire thicker. So having a thicker wire will allow electrons to pass through more easily, and less collisions will occur, and there'll be less friction, therefore less resistance. Number two, use a better conductor. So choose the right material, choose the best metal to allow electrons to flow through with as little resistance as possible. Okay, and copper tends to be the best metal for that, for electrical wires. And finally, we can cool the wire down, so reduce the temperature of the wire itself. And the reason for that, all these positive ions can do inside a wire is vibrate. They can't move, they can't slide past one another, they can only vibrate in fixed positions. Now, if the temperature of the wire gets a little bit higher, then those vibrations are going to be greater, and they're going to slow down the electrons passing through even more. So if you cool the wire down, you reduce the temperature of the wire, then those vibrations will become less and less, and the electrons should be able to pass through a lot easier. So again, reduce the temperature, reduce resistance in a wire. Use a better conductor, also reduces resistance, and finally make the wire thicker, which also reduces the amount of resistance and the collisions basically between electrons and positive ions inside that wire. Okay, so that's all you need for 10F. Obviously rearranging these equations as well. For P equals energy divided by time, time equals energy divided by power, and the same in this one. If we want I, it's E divided by VT. If we want V, it's E divided by IT, and if we want T, it's E divided by IV. Okay, moving on to 10G then on power. Same equation as before, but I've rearranged it for power P. So power equals the energy transferred divided by the time taken, the units of which are watts, capital W, and all that means is the power of a device is the amount of energy transferred per second. So how many joules per second are transferred by a supply or a device or component. E equals IVT, which we had in 10F, and we're going to create two new equations of power based solely on these two equations. Okay? So first of all, if I know that power equals energy over time, and I rearrange as I did over there, energy is power times time, then I compare it to this equation for energy, which is energy equals current times voltage times time, and I compare this one to this one. I have energy equals, and I have times time times time. So basically the only difference between these is the P power in this one and the IV in this one. It's E equals something times time, E equals something times time. They must be exactly the same. So that means P is equal to I times V, which is this new equation here. So another equation for electrical power, current times by the voltage. Okay, so you may be required to do that. Moving on from this, looking back at 10D, we had an equation for voltage which was V equals I times R. Now if I look at this equation, power equals current times voltage, I can create a new equation for power. If I swap, for example, let's say in the equation in the exam, I have been asked for power, I have current, but I don't have voltage, I may have resistance. So P equals I times V, but if I have V equals IR, then I can swap the V here for the V here. So P is equal to I times V, but V is IR, so I put the IR, just substitute this for V in here, and that gives me P equals I squared R. There is another equation for power that you are expected to remember in the exam. So P equals energy over time, power equals energy over time, you need to remember. E equals IVT is actually given to you at the back of the exam. P equals IV, which we took out of this equation and this equation, so we rearranged and substituted to get P equals IV. You must remember this one. And then we use V equals IR, which also has to be remembered, and we created this P equals I squared R. Okay, they're all the equations for electricity that you have to remember. This one's given, this one you have to remember as well. Okay, and that's it.